Hi everyone. We will begin the ATSP seminar. Today's speaker is Zhenbin from the Stanford University, and he will move to the China SITP in the 2023, and he will talk about the late time behavior of OTC. Please welcome him.
All right. Yeah, thank you. Thank you for the invitation. Today, I'm going to talk about some work that appeared last year with Douglas Stanford and Shunyi Yao. There's a related work later last year by Gu Kitaev Zhang. So the work is about the late time behavior of Otoc. Before talking about the main topic of this talk, let me first give a lightning review of quantum chaos. Otoc is a sub-branch of physics in quantum chaos, so let me first try to review the broader aspect of quantum chaos. So these days, when we talk about quantum chaos, we usually have two different, slightly different concepts in mind. So first is about single particle quantum chaos, and the second is about many body quantum chaos. So theory about single particle quantum chaos has been developed for last 30 or 40 years. And the many body quantum chaos is a new subject. Essentially, people become interested in the recent 10 years. So let me try to first give you a review about single particle quantum chaos, the traditional theory of quantum chaos. That studies a quantum theory of classical chaotic system. So study the quantization of a classical chaotic system. I think it was Einstein who pointed out that it's not that trivial to do a quantization of a classical chaotic system because the equation motion in quantum mechanics, the Heisenberg evolution essentially is a linear evolution. And the classical chaos, it mainly comes from the nonlinearity of the classical equation motion. So it's quite non-trivial to ask the question, so how to say a nonlinearity in a linear Hamiltonian evolution? And the answer is provided that essentially in the quantum system, the classical chaos is encoded in the energy level statistics. And that has been made precise using periodic object theory. So here on the left-hand side, we have a typical classical chaotic system. It's a particle moving in a billiard. It's an irregular billiard, so its trajectory is chaotic. We can characterize its classical chaos by looking at how two trajectories that are very close at the initial location can deviate with respect to each other. If the deviation at late time grows exponentially, we call it classical chaotic system. And the exponent, we call it as the Lyapunov exponent. That's a classical butterfly effect. In the quantum system, we expect that this classical chaos is reflected in its energy level statistics. So, for example, the spectrum form factor, which basically is a product of the two analytic continued Poisson function, encodes the energy level statistics. And the effect of the classical chaos, it will be translated into the late time behavior of the spectrum form factor. So here we plot a spectrum form factor of a GOE ensemble. And if its late time behavior, it has a linear ramp and a plateau. Those features are related to the classical quantum chaos in a precise way. So one can say that what encoded in the quantum system about the classical chaos is this late time behavior of the spectrum form factor, this ramp and plateau physics. So this connection is made precise using the Goose-Wheeler-Chase formula, which represents the density of states, rho of E, in terms of sum of the periodic orbits. So here, gamma is a periodic orbit that start and come back to the same location. And the Goose-Wheeler-Chase formula essentially is like a semi-classical quantization of the path integral, express the density states, rho of E, in terms of sum of periodic orbits gamma with a weight that is weighted by its classical action. This S gamma is a classical action of the periodic orbit gamma.
And gamma is already in the phase space.
In the phase space, right.
Okay. So it should be periodic, or
yeah, it should be periodic. The initial momentum and the position should agree with the final position and momentum.
Okay, is there a case that where it's not periodic, like
no
chaotic? No. Okay.
Yeah, this equation coming from writing. So you know that rho you can write as an imaginary part of the resolvent. So it's like a trace of the Green's function. So basically, you use semi-classical approximation of the Green's function as like a sum of classical orbits, and then the trace enforce its initial and the final location be the same, and the momentum to be the same. So that's coming from the definition of the density of states. So this is a formula writing a quantum object, the density of state, in terms of a classical quantities, which is valid in the limit when h bar is very small. And then the theory initiated by Barry showed that those late time spectrum form factor intermittently related by to the classical orbits. For example, if this spectrum form factor have two patching functions, so each contain a rho, so it's a 2-point function of the rho density correlators. So it involves two traces. So it involves some two orbits, gamma and gamma prime. And Barry showed that if you choose gamma and gamma prime to the same, which he called as a diagonal approximation, then this recovers this linear ramp behavior. And then there's correction to the linear ramp, not in GOE, but like a GOE system, GSE. And Cyber Richard and later these folks show that you can consider a slightly off-diagonal sum in this double sum, which they call this as the encounter geometries. Those give you correction to the linear ramp. Okay, and to get Plato is more non-trivial, and I'm not going to discuss that. So that's a roughly review of the classical quantum chaos, the single particle quantum chaos. Basically, it's talk about the orbits of a single particle moving in a billet. So that has been well developed. Nowadays, when people, when in Henry community, we talk about the quantum chaos, we usually often have in mind of a many-body quantum chaos. And we become interested in it because the many-body quantum chaos have a close relationship with the quantum information theory. It describes the information scrambling, and it have an intermediate connection with the black hole physics. So one of the main subject quantity that play a dominant role in many-body quantum chaos is so-called OTOC. It's called out-of-time order correlator. It basically is a quantum generalization of the this commutation relation, of this deviation of the later final position by initial position. It's a quantum generalization of the butterfly effect. You can think about this OTOC is describing the the two norm of this quantity. So if you are a quantum system, you replace this Poisson bracket by a commutator. And because it's an operator, to measure this deviation, you choose a norm. So let's choose a two norm. Then if you expand this two norm, you will find the dominating correlator describes the Lyapunov behavior is OTOC. We call it OTOC because the ordering of the operators are not conventional. We have W at t equals 0 and V at t, and then back to W at t equals 0 and V at t. So it lives on this OTOC contour. Here, this 1, 2, 3, 4 are the time contours. So we can think about this one described given by a time evolution e to the IHT, we insert a V, then e to the minus IHT at 4, insert W, e to the IHT, V, e to the minus IHT, W, and trace over. So that's this contour describes this OTOC. And in gravity, this OTOC, the physics of this OTOC is related to near horizon shockwave scatterings discovered by Schenker and Stanford. And in typical system, in a many-body chaotic system, we expect this OTOC have the following behavior. At the early time, because V and W can, we imagine V and W at different locations. So at the early time, there's no causal inference. So we can commute these two operators. And we can, its answer is given by the product of two two-point functions. So we can normalize it as a constant 1. And then the butterfly effect describe this OTOC should have exponential growth. So its deviation from 1 grows exponentially, e to the lambda t. So this is exponential growth. And lambda we call as a Lyapunov exponent. And there's an overall 1 over n effect coefficient for a system with degree freedom n. So if the system have a local degree freedom n, the OTOC should have this early time exponential growth. And when this quantity is order 1, so this exponential growth piece is order 1, that meaning t is order log n over lambda. We define that time scale as a scrambling time. We call it t star. That's a scrambling time. And today's talk will talk about what happened to the OTOC after the scrambling time. The physics after the scrambling time. So this OTOC has been recently discussed in many contexts, including the page curve, hidden Presco black hole mirror, shockwave we discussed, and the chaos bound, traversable wormhole, operator size growth, etc. So those have a lot of fascinating physics associated with OTOC.
So early time, it's constant because, as you said, the V and W is commute, almost commute. So
right.
It's factorized, but the later time, like after this scrambling time,
right,
around this order, or why it goes to 0 is what is the physical meaning of.
Right. So the physical meaning you can think about it the following. So this Heisenberg operator V of t, because Hamiltonian is chaotic, so that just makes the simple operator V as a sum of the non-local operators, and so it will have like a overlap with W when you expand it, and then its overlap component with W. The component grows, and that basically is the effect that this have the exponential growth. And on the contrary, if it's like an integrable system, the V of t will remain to be a local operator. So it will just like in a quasi-particle, the particle just transport to another particle. So they will still approximate commute. So you won't see this effect.
So maybe maybe my let me change the question. Why it's minus, not the plus? Is there some?
Why it's minus?
Yes.
Right. So because it's an overlap between this WV. You can think it's an overlap between these two states, and the overlap is always smaller than 1. So the 1 is the norm of the state. So if you like, instead think about this as a bra and as a cat, it's an overlap between these two states. And the early time is the normal state is 1, which is
okay. But it's okay.
Elementary question. So sorry, I just missed the scrambling time. Will you repeat again?
Right. The scrambling time is when this negative term becomes order 1. So that is t equal to log n over lambda.
So what does it mean?
It means this correlator basically becomes very small. So OTOC basically decays to 0.
So you mentioned that in non-integral system, V and W is much renormalized. I mean, they become more complicated object as time goes on.
In a chaotic system, right?
Yeah, in chaotic.
V becomes more complicated, right?
Then the overlap of this WVT and WVT then much decreases.
Yeah.
Then I see.
Right. Right.
Okay. Yeah. Thank you.
Right. And if you look at it as a commutator, it's a norm of this commutator. Then you find this norm is basically 1 minus this quantity. So that describes when this commutator, the value of this commutator saturates. That's basically what the scrambling time means. Right. Because the commutator at early time is 0, V of t and W is 0. At the early time 0 if they're like different correlators, and time goes on, their overlap becomes large. So this commutator becomes non-zero, and that behavior is described by this 1 minus this quantity, so it's described by this exponential growth, and the scrambling time is when this quantity saturates.
Thank you.
Right. Okay. This I will not talk about it, but just for completeness of this talk. So recently there have been also understanding what's in gravity system, what's describe this random matrix behavior, this linear ramp, and there's gravity understanding of this linear ramp. It's coming from some wormhole geometries. And in our story, at late time of OTOC, there's also a wormhole contribution that is important, that we will discuss later. So we will talk about the late time behavior of OTOC, and in particular after the scrambling time. So we already discussed at t order the scrambling time. Here I think I is roughly at this time value, it's a scrambling time. We want to ask what's the behavior of the OTOC after the scrambling time, and what's the physics associated with it. And we will talk about there are 2 characteristic behavior. So first is immediately after the scrambling time, the OTOC coming from change from this exponential growth to exponential decay behavior, e to the minus 2 lambda 2 delta t, where this delta is depends on what operator you're using. It describes basically the quasi-normal mode of this operator in gravity theory. And then when this decaying to 0, then you find that at even later time, the OTOC have approach to asymptotic to a negative value, minus e to the minus n. N, remember, n is the degree of freedom of the system. So it's a non-perturbative effect. And we would, so the talk will be divided into two parts. The first part will talk about this exponential decaying piece. Actually, it will talk about this whole transition regime from exponential growth to exponential decay regime. And we will discuss it is controlled by a quantum coherence effect, quantum interference effect. And then we will talk about the next part, this negative nonperturbative small effect. And this effect is determined by the random matrix universality, and we will argue that this effect coming from a wormhole contribution to OTOC in gravity. And in many body system, it's a nonperturbative saddle point contribution. It's an instantaneous contribution in a ordinary many body quantum chaotic system. Yeah, question?
Yeah, I have question here. Delta, it seems that here usually OTOC is reaction exponent is kind of universal. It's a kind of independent of the choice of the operator. But now later,
Right.
Does it depends on the operator?
Right. Exactly. That's the point I want to make. This lambda is independent of the operator. It depends on the system. It's a coupling constant. This delta depends on what type of operator you introduce to probe the OTOC.
I see. So even though it's chaotic system, somehow this operator can be
right.
It's the characteristic of the operator survive. Okay, I see. And the next question is
then the late time behavior does not depend on the operator again.
So also the OTOC calculation, there are a lot of other many contributions. So is it also still the leading behavior, and there is also a lot of behavior suppress a lot, or
sorry, could you
in the reaction exponent the calculation, so there are many other contribution, but in the end this is leading contribution to the
yeah, there's a leading, right. There will be some one over n pieces that it's like further correction to these behaviors, right?
I see. This is kind of correction also. Is it also leading this e to the minus 2 delta t is leading?
Yeah, so it's e to the minus, yeah, it's a leading effect. It's coming from a resummation of this 1 over, so there in particular there will be like 1 over n squared e to the 2 lambda t corrections, etc. This is coming from resummation of all those effects, giving me this e to the minus 2 delta t, and that's a leading effect. Right.
Thank you.
Right. So as I described, so the part 1 will describe a universal theory, describe this nonlinear regime. It's nonlinear because it's this coming from summing over this 1 over n squared, 1 over n cubed terms, and it's coming from a quantum interference effect. And the part 2, we'll talk about this late time behavior is coming from instant contribution. And in gravity, it's related to wormholes. Okay, so now let's talk about the first part. To talk about first part, I want to basically trying to argue that the definition of quantum chaos indicates a special feature of the OTOC contour. In particular, it indicates there's special pair of soft modes living on OTOC contour. So we are interested in the OTOC, which is like a 4-point function on this out of time order contour. And we can view it as a special correlators living on these contours, and we do a path integral on these contours. So when we do a path integral, we can what we can do is we find the saddle point of this path integral. Path integral is the integral, so we can find a saddle point on this path integral, and then do a mode expansion, integrate its one loop mode. And here we are argue that the OTOC quantum chaos means doing this procedure, there's a soft modes living on this OTOC contour. So let's have a look how they are connected. So quantum chaos means small initial perturbations can lead to a large change of the field configurations, which grows exponentially in time. So if we have on this saddle point of this OTOC contour, we have some value of phi. Now, if we introduce a pair of operators, then the field variable will have some correction proportional to the amount of operator we inserted at the initial time. This amount of change, this response, we call delta phi of t. And if it's chaotic, that means this delta phi grows exponentially, which describes the decorrelation of these two sides. So delta phi grows e to the lambda t. So it's a field variable living on this OTOC contour, and we can view it as a special mode. We will call it as a Scrambling mode, labeled by X. And as a mode, any mode, when we do the path integrals, you should normalize it so that its norm, the Hilbert norm of this mode is order 1. And since it grows exponentially, that means you want to normalize this delta phi such that at late time, it's order 1. At the final time, delta phi at capital T is order 1. Capital T is late time behavior. So that means this delta phi really comes with exponential small coefficient. In other words, quantum chaos means this Scrambling mode X can be excited with exponential weak source, e to the minus lambda t weak source. That means that this mode is exponentially soft, since it can be excited exponentially with exponential weak source. And there are two such modes due to the time reversal symmetry of the system. We can either introduce an operator at the initial that introduces X mode, or we can introduce a late time operator that introduces a mode that's growing to the past. We call these two modes as X and Y. And the action cannot depend only on X or Y, because if only one mode excited, then there's no operator insertion in the future, it will cancel. So just by unitarity. So that means that the action can only depend on the product of X, Y, at least at the leading order. And both are exponentially soft. That means the coupling constant of this mode is exponentially small. And in a many-body system, the action will be proportional to the degree of freedom of the system. So that's the factor of n in front. So that's prediction. That means quantum chaos indicates that on this OTOC contour, there exists an exponential weak pair of soft modes, X and Y. And this is valid for any many-body chaotic system. And in particular, in gravity, this action is called the J-Toft action. So basically, J-Toft derived using in general relativity that near horizons there's such a type of action. And here we argue that this type of action actually valid for a more general chaotic system. Without
here,
gravity.
so here, this is a kind of in the field theory side, you are consider Schwinger-Keldysh formal region with some insertion of
with four contours. The Schwinger-Keldysh with forwards, backwards contours. And then, so usually when people talk about Schwinger-Keldysh contour, people talk about hydrodynamic mode on this Schwinger-Keldysh contour. Here, we argue that on this OTOC contour, on this OTOC shrink Kaddish contour, if the system is chaotic, there will be the special hydrodynamic type of action that is determined by the Lyapunov exponent. That's a very robust prediction. Right. Just draw a picture that people can understand this X and Y mode. So here, let's imagine we associate some meaning about the relative location of these contours. If they're close, we imagine their correlation is large, and if they are far, we imagine their correlation are small. So then the X mode is excited by the initial perturbations that describe a pattern of correlations that destroys those two pairs. So remember, this is one, this is one, and this is two. So the X type of correlation, they construct the correlation between X and 1 and 2 contours. But it leaves 2 and 3. The correlation between 2 and 3 is still large because there's no operator insertion in the future. And the fact that X grows exponentially means this correlation, the deconstruction of this correlation grows exponentially. You can roughly think about this as like a cartoon of how a particle in a billiard looks like. So if we have the initial perturbation, these two initially closely parallel trajectory deviate exponentially. But here it's a many-body system, and so we instead of discuss its trajectory, we are thinking about these correlations of the time contours. And this is the X mode, and the Y mode is excited by the late time correlators and describe the correlation between 1 and 4 or 2 and 3 decays. And in particular, this deviation grows exponentially. And we are saying this OTOC contour, this 2 mode are the leading mode. It's exponentially soft with the action given by the straight of the back action. And in order to this, so for example, we can, as we said, this X describe a deconstruction of correlations. So that can be measured by looking at the correlators on this background. So we can look at the correlators on these 2 sides with the non-trivial X excitations, and this correlator will decay with respect to time. And that probes this X. And here we can insert a W correlators on these 2 sides and look at how the correlator becomes smaller and smaller as time gets earlier. And we will find this correlator basically decays. And we will label this correlators on the background as VVX and WWY. So if we put the V at the late time, at the end time, that describes the pattern of correlations here. And WWY is the pattern of correlators. And right, the scrambling destroys the correlations. That means VVX, when X is large, goes to 0. Same for WWY. That's what the X and Y mode did. So this is a general theory I argued, and here I will describe a particular system where I can make everything I said before precise, and that is a Brownian SYK system. The Brownian SYK system is a quantum mechanics system made out of n Majorana fermions. We call it psi AI. So AI runs from 1 to Q. 1 to N. It's n Majorana fermions. The Hamiltonian is a R2R interacting Hamiltonian with a time-dependent random coupling constant. So the coupling constant J have a mean 0 and the variance that non-zero only at equal time. If the coupling constant J is independent of time, this is a SYK model, and it's Brownian. If it depends on time locally, then we call it the Brownian SYK. And this is first discussed in this paper. So it has several properties. So first, it's chaotic, since it's R2R. And as a SYK system, this theory is dominated by Melonic diagram. So those are, for example, if you look at the 2-point function, then the Feynman diagram of the 2-point function is dominated by these Melonic diagrams. So this solid line is a 5-5 propagator, and this dashed line is the JJ propagator. And so all the dominating diagrams are those Melonic diagrams. And third property is basically this Melonic diagram dominating feature determines this theory can be solved exactly. Third is it has time-dependent coupling constant. That means there's no energy conservation. And so there's no free parameter because you can absorb the J by a definition of time. And at late time, the theory approach a random unitary evolution. So we're going to study the OTOC of the system after the scrambling time. And to do that, we will, our strategy is put the system on the OTOC contour and do the path integral. And when we do the path integral, using large M, we consider the system when the number of degree freedom n is large. At the large n, the path integral will be dominated by a saddle point approximation. And basically, the saddle point approximation gives you the shrink depth equation, which is the Melonic diagram theory. So what we're going to do is to study the theory path integral using saddle point approximation and study its one fluctuations. And that generally will give us a good answer for the OTOC. So to view this path integral, we will view this OTOC contour in the following way. We view it as it's a path integral of a 4 copy of the system. 1, 2, 3, 4. 1 have a Hamiltonian h, 2 have a Hamiltonian minus h, 3 have Hamiltonian h, 4 have Hamiltonian minus h. And the OTOC imposes certain special initial and final boundary condition on these 4 copies of the system. And when we do the path integral, we will introduce some mean field variable and the mean field variable is a correlations between these 4 copies of the system. So X denotes a correlation between 1 and 2, psi 1, psi 2. Y denotes the correlation between 1 and 3, and Z denotes the correlation between 1 and 4. So the path integral will be written into the path integral in terms of X, Y, and Z. And the saddle point, I'm not going to write down what the path integral looks like, but I'll just tell you that the saddle point of this path integral gives you the shrink depth equation. And in this particular Brownian SYK system, it's particularly simple. It's a linear ODE equations. Sorry, it's an ODE equation, but non-linear. It's 3 equations written as a derivative of X, Y, Z in terms of linear product of Y, X, Y, and Z. Yeah, question?
So here, what is this Boltzmann factor insertion? So is there some particular insertion of Boltzmann factor, e to the minus beta h over some factor in this contour?
Sorry.
The Boltzmann factor, e to the minus beta h factor. So how did you insert in this?
No, you do not
control?
insert. So there's no e to the minus beta h. So because there's no energy conservation, so there's no notion of temperature. So just insert it with infinite temperature, beta equal to 0.
Oh, I see. So here, it's also maybe it's also the economic advantage also.
It's also
is there
fixed. Just
fixed?
Yeah, it's only determined in terms of Q.
Oh, I see. So what about this bound here? Maybe it's not non-unitary. So
Right. So yeah.
I see. Okay. Okay. Thank you.
Right. Right. So this is the shrink depth equation, and to study the OTOC, for example, just for convenience, let's consider the OTOC, the initial and final insertion using this operator insertion in the exponential. Then this boundary condition we introduced translated into some special part of boundary condition for this x and z, x, y, and z. So given this OTOCs with the shrink depth equation as this boundary condition, we can solve the shrink depth equations and evaluate this OTOC. And that's what the procedure we're going to do. So let's look at the numerical solutions. If the t is smaller than scrambling time,
Question?
yeah.
Let me try to, frankly speaking, I think I'm lost about this part. So without any insertion of either V and W, we know so how the Mellon diagram is given by the saddle point solution for large and limit. Then around this background, so you can I say. So will you some more figure out how you obtain x and y in this differential equation?
Right. I'm not going to discuss here because of time. But basically, what you do is the following. So you write this in terms of, let's see whether I can annotate here. So you have this Hamiltonian, right? So you can write your theory as path integral of d precise with e to the I ht, right? Okay, and then what you do is so because this h depends on this coupling constant j, so you can first average over this j.
Yes.
So that gives you some like some psi. Sorry. The psi, and then they'll give you some like because of the average, so that gives you some like psi to the psi a1 to the aq and q, and then another copy of psi a1 to the aq, right?
Yes, right. Yeah, then we can decompose the sigma g blah blah.
Right.
Then,
right. Then there's then you introduce this correlations of this g and sigma.
Yes.
Right. And where the g is in terms of psi correlators, right?
Yes, right.
And because this OTOC contours, this g has the contour index, basically this 1, 2, 3, 4, right? So, so the g has some big contours, and x, y, z is its component.
I see.
Of the g.
Okay.
Right.
Thank you.
Oh, sorry. I just. Yeah, thank you for the question. Yeah, just ask me any question if it's not clear. And so basically, this is a G sigma equation, but because in Brownian SYK, it actually simplified just in terms of linear. Sorry, in terms of ODE of this actually. Basically, if you have studied SYK, then you can this is a G, derivative of G, and then this is sigma, like I already use the equation motion of sigma equal to g to the q minus 1. Basically, that's this what this equation looks like. Yeah, thanks for the question. All right, and just coming back to the question about the initial and about the Euclidean time. So let's consider if there's no operator insertion. So here, because there's no notion of temperature, so this will be an EPR. So the initial and the final condition will be an EPR pair between 1, 2, 3, 4, and 1, 4, 2, 3. And then with this insertion, it's like some extra rotations on this EPR states. So now what we are going to solve is solving the shrink depth equation, the G sigma equation, numerically. So let's look at the numerical solution. If the time is smaller than scrambling time, then you will find that the X, Y, and Z correlators have this form that are compatible with the boundary condition. So let's look at the feature. So X is the maximum at the early time, then have this exponential growth. And Z stay as a constant at a late time, and then have exponential growth to the past at the early time. And Y up to this sign basically is like the minimum of Z and X in its absolute value. So we can think about it's the following. So when we introduce these red operators that introduce some scrambling between 1 and 2, and this affects growth, and that leads to this X correlator decays. And this late time insertions that will lead this 1, 4 correlators decays at the early time. So that basically is this effect. And if we plug this in, we got this Lyapunov growth in the system. But we're interested in the behavior after scrambling time. So here there's some interesting feature of some spontaneous symmetry breaking happens. So after scrambling time, we'll find there are 3 saddles. One saddle is basically it's like a continuation of this saddle. If we make this window a bit larger, then we got here. So basically this before scrambling time is this small window, but if you make it larger, you got this one. So basically describe when X and Z correlators decays to 0. So pictorially, you can think about describe this pattern of correlations. So this Z goes to 0 and this X goes to 0. But there's 2 other saddles. There's this one, and then there's like time refraction of this saddle. This saddle breaks the time reversal symmetry, right? And describes a solution with constant X insertions. And we can think about it as the following, because here we're considering its operator insertion in the exponential. So even when at the initial time, the correlation between 1 and 4 goes to 0, this operator insertion just gives you an identity. So basically, this saddle describes effect that if we have some late time operator insertions, its effect dominates, so it deconstructs the early time correlation fully. And then if we insert these red operators, because the correlation already deconstruct, it's the same as the insertion identity. So it makes no difference. And that therefore it does not makes X correlation small. And another saddle, which is time reversal. So the X time at the early times, this red operators fully deconstruct the Z type correlations. And when we insert this Z type of operators, it does make no effect. And this middle saddle is described by detailed balance between these 2 forces, where each one wants to deconstruct their correlations and then its effect also getting smaller. So it's a very detailed balance between these two effects. Basically, the red want to kill the effect of the blue, but then the blue want to kill the effect of the red, and they can balance each other unstably. Okay. Now to look at the OTOC, we already get the saddle point, and we just need to do a one loop analysis to get the OTOC. So for the correlator before the scrambling time, we do a one loop analysis. Then you find that there are two dominating modes around this saddle. That is determined by shifting the center of this hump and then changing the width of this hump. It's a symmetric and anti-symmetric saddle. And both the symmetric have a positive exponential small eigenvalues, and the anti-symmetric saddle have a negative exponential small eigenvalues. And those are the soft modes I described at early time. In particular, since we already use the XY for the correlators, so I will call the two soft modes as X plus and X minus. So X plus and X minus is basically the sum and difference of these two modes. And if you plug in their value of eigenvalues, you get this effective action I described. And so at early time, this effective action, the coupling constant is bigger than 1 because T is smaller than log n over lambda. So this coupling constant is larger than 1. So we can just do a one loop analysis to get this OTOC. But we already see that this set point approximation breaks down after scrambling time. So in other words, if we look at the set point one loop fluctuation around this saddle, we find that the one loop fluctuation is large and the coefficient is smaller than 1. So we cannot do a one loop analysis. We need to go to higher loops. So essentially, it tells you that we cannot charge this saddle points. And that's what I mean. It's a quantum interference effect is important. So but based on our general argument, since what breaks down is this two scrambler mode, X plus and X minus. So we just need to treat the path integral of this two mode exactly, and the others we can still do a one loop analysis. And treating this two soft mode exactly gives us this effective action in terms of this X plus and X minus. So this is the same as the action on the OTOC contour. And these two terms are basically it's the initial and final operator insertions that just on the X and Y mode. Notice that its coupling is proportional to gamma. So that's these two terms. So in particular, this first term is this late time operator insertion, and this term is the early time operator insertion. One is coupled to the X plus and one coupled to X minus. So you need to work it out how the correlator depends on X plus and X minus, which you can do by solving the Schrödinger equations. I'm not going to do here, but that's what you got. It has this simple form. And if you look at this effective action, look at the saddle point approximation, indeed, you'll find that at the early time, you got this saddle, and at the late time after scrambling time, you got some spontaneous symmetry breaking phenomena. You recover these three saddles. They match numerically very well. So that really tells you that this effective action actually controls the solution of this Schrödinger equation. And so we just need to do this path integral. And And here's the result. So here we are. Here, in order to compare with the numerics, we look at the operator insertion, not in the exponential. So that's just to do a linear perturbation of the gamma, just drop down these two factors. That's these two factors. And this is the action. You can do this integral exactly. It's write into some hypergeometric functions. It's a sum of this 1/n effect, 1/n square effects, etc. And you got this blue curve. And in this paper, they did the exact diagonalization in Brownian SLK up to n equal to 10 to the 6. The red curve is what they got numerically. And we just plug this value in. You find they match exactly. So that gives you some confidence that this formula really describes this OTOC across the scrambling time. Notice that this result is valid after scrambling time, which is when this this coefficient is smaller than 1. So that's coming from the set point approximation of the effective action breaks down, but we are doing the exact integral, so the result is still valid. And yeah.
I have a question here. Any 10 to the 6, then the size of the Hilbert space is 2 to the
2 to the 2 to the 2 to the n, 2 to the n over 2, right? So you cannot do it with direct diagonalization, but what those guys find out is you can map this OTOC into some correlator in some other Hilbert space by mapping to the choice state. And the other Hilbert space, there are some symmetries. You can truncate this Hilbert space. And so with like even just a normal computer, you can run a very large M compared to Brownian. Right, that's what this paper did. And this formula is first described in our paper and then later recovered in Guki-Davidson paper. Okay.
Question?
Yeah.
Can I see one page before? So
which paper?
Yeah, here.
Which page?
Here. Yeah. So I think I'm lost. So
right.
I can follow. I can understand up to the given saddle point XYZ, and I infer some perturbation of the second order as usual as
Right.
and for the G sigma case, then I can obtain some Swaranskian blah blah. But here, so how can you find some infinite order result, the 1 over x plus this kind of term?
Sorry, this kind of term?
Yeah.
Right. You ask how do I find this? Term?
Yes.
Right. So yeah, basically this term. What is this term? This term describes the correlators basically describe the correlators on the background of x or y excitations. So basically, this is described as VVX and WWY. So you want first insert some x operators to excite some finite amount of x, and you look at its correlators on this time, depends on it. So basically it's a VVX, right?
Yes.
And what you do is you just insert these correlators. So we know that the initial operator insertion will excite this X mode, and you do not insert the late time correlators. So that means you do not back react on these X insertions. And you just look at the back reacted Green's function, G. Do I make myself clear? So technically what you do is you insert this in 2-point function on this OTOC contour. You solve the G sigma solutions and look at its value at late time. That's what this 1 over 1 plus x plus to the 1 over q minus 2 comes from.
I think I don't understand. So usually, I mean, given saddle points, then I introduce some fluctuation around delta G, delta sigma, then I will obtain some Swarupian and so some
Right.
collective mode, some up to
Right.
the one loop, as you mentioned, the first expression, and
Right.
x plus x minus product. So here,
So you have some saddle point of G and sigma.
yes,
Then the Schwarzschild give you some like related to is parametered by some value f, give you some GF, right?
yeah, basically delta G, delta sigma, yeah, whatever, yeah, up to the
Sigma
second
F.
order, yeah, yeah.
Right. And then you look at the action that depends on f, you get some Schwarzschild of f, right?
Yes, right.
And you get some value. Okay.
Yeah.
So here there's no well, in the Brownian network, there's no clear Schwarzschild, and but here what you do is basically you have G and sigma, and you have this x plus and x minus mode, plus minus. So you look at the Green's function in terms of parametered as by the x plus and x minus, right? So that G of x plus and x minus is these values, as those values. And
So-
you look at the action depends on x plus and x minus. So the analog of the Schwarzschild in this case is this action. So this is the analog of Schwarzschild, and these two are the external coupling on the Schwarzschild, on the x plus x minus. Sorry.
I see.
Right. Yeah, here it's more simple because Schwarzschild it's a field that are living on the time, so that depends on t. But here it's really just two constant mode. So it's a dramatic reduction. So in other words, you can, if you have Schwarzschild on the OTOC contour, then you will find that you will have some f that will depend on x plus and x minus. So you can also get the same action by reducing the Schwarzschild, looking at the dependence only on x plus and x minus. That will also give you this effective action.
Thank you.
Mm-hmm. Yeah, sure, no problem. Right. Yeah, few remark. So this is the type of pattern of this effective action looks like, and we can do a Fourier transformation to go to the dual variable p and q due to x and y, and then in gravity you can, this formula has the interpretation as Eikenhofer summation. Here this is a scattering S matrix, so e to the is, and this is the Eikenhofer summation near the black horizon. And the same action derived later by Gu, Kitaev, Zhang using ladder diagrams. So basically, they argue that any theory that dominated by ladder diagrams will give you the same effective action. So their derivation is more general than what we did in Brownian SYK. And our argument, although the general argument we give at the beginning is more general than what they did. And it's a quantum interference effect coming from integral of x and y mode. I think I probably, how many times do I left? I think I probably go over.
It's already over, but you can like keep going like until like 10 minutes because it is lunch time, so we can still have time. Yeah.
Okay. Yeah. I will try to finish this second part very quickly. Yeah. So the effective action we discussed before describes the behavior of OTOC near the scrambling time, past the scrambling time, and then, but that answer is eventually decays to 0. So you look at this answer, eventually it decays to 0. And but the OTOC at this time, actually, we expect that it approach to nonperturbative small f constant. And this is determined. This we expected from the following approximation. So at the very late time, we can approximate this e to the IHT, this time evolutions, as a random unitary evolution, which is a pretty good assumption for chaotic system. And if we do a random unitary, do a high average of the system, then actually random unitary average tells you that late time OTOC have approach to this nonperturbative small effect result. Here we assume the one-point function vanishes. So all these terms, so all those terms goes to 0. And the random unitary theory predicts that late time it approaches to negative answer. Here L is the dimension of the Hilbert space. So L is e to the n. So this is like quantum mechanics derivation for this late time behavior. And we want to see it more geometrically using path integral. So, this is some derivation of the late time Weingarten calculation. Let me not discuss it due to the time constraint. So let's look at what happens at late time in Brownian cycling. So if we take the time much larger than the scrambling time. And what you find is that you have some additional saddle contribution. So this is one of the saddle that give you the negative term. So this saddle point describe correlation where you have some constant value of z, and then it decays, and at late time it grows back. So this behavior that the correlator of z vanishes, decays to 0, is easy to understand. Basically, because we have this v operator insertions that make this this is x. This is v type of insertions makes this z type of correlation decays. So we can view this decay as coming from here. Basically, this is the z correlations that goes to 0. But when after it stays to 0 or sometime, somehow these z correlators can recover to its maximum value and stay as constant. And so you can think about this recovering as coming from encounter structure. That is, somehow, if we think about those are some particles in a billiard, so this z correlators describe two very far decorrelated trajectories, but then they can have some little chances that they happen to line up each other and come back to itself again. So that describes this correlation. So this describes the z correlations. It was very far from each other, but somehow, by some small chance, as time moves on, they can come together to each other, and then they stay together to each other for quite a long time. That's this saddle. And similar for x, the x correlations at early time decays to 0. That's because of this early time insertions that makes this x correlators goes to 0. So the distance very large. But then this 1-2 contours are very far from each other, but somehow they can come in very close to each other. So that gives you this 1-2. And after they come very close to each other, they stay as a constant. And that describes the value of x. And their behavior constrains the value of y to be this form. And so that's what this saddle looks like. It basically corresponding to these two. So originally, before we have these two type of patterns, but then here the additional saddle coming from adding this additional structure in the middle that describe a transition of the pattern of correlations between them. And due to the fact that it's unlikely these two, this 1, 2 getting close to each other, that basically gives control that its action is suppressed. So if you evaluate the saddle point classical action for this saddle point, you find it's exponentially small. It's e to the minus n. And you've similar as the previous discussion, you have some large fluctuations associated with the hump. There's this symmetric mode describes the size of the hump and the location, the anti-symmetric mode, the x plus x minus mode. And you cannot trust saddle point approximation. And so you need to do basically a full quantum analysis of this saddle of this x plus x minus mode that moves this hump. And here's our conjecture. Our conjecture is that its action is of this form. So, sorry, its action is not a conjecture. You can derive it, its action explicitly, but our conjecture, but you need to work out the integration contours. And here our conjecture is this integration contour is lying on the principal branch of the integration contour, where x plus and x minus is not equal to 0. When they equal to 0, describe the hump annihilate with one or the other end, and there we do not expect this saddle point, this soft mode still exists. And if you do this integral, you find it's a negative term, -1. Okay. Yeah, how do I? Right, and this evaluate this saddle around saddle point contribution that give you this late time OTOC term. We can justify this conjecture in GT gravity. In gravity, we know which is due to low energy limit of SYK, and the corresponding geometry for this saddle point is described by Handel disk geometry. So it describes this V and W particle miss each other through a wormhole, and because it's miss each other, there's no scattering. That's basically the result. Why the result proportional to product of two-point function VV and WW. And this 1 over L squared coming from adding an actual handle, actual genus in this geometry that gives you the 1 over L squared. And then there's scrambling mode, scrambler mode, integral, this x plus and xy minus mode, which you can derive explicitly in GT gravity. Those associated with the length between this the proper length around these two cycles. And the integral gives you the -1. So that gives you this late time behavior of the two-point function, OTOC. So that's it. So in conclude, we talk about the late time behavior of OTOC. And at this time, we find that this nonlinear regime is described by universal action. And here, this scrambler mode is very important and describe basically a fluctuation of the contour of this form. And then we also describe the nonperturbative contribution to OTOC. And those coming from basically the some encounter structure in this correlations. And again, this scrambler mode play a dominating role. And that's it. Thank you.
Thank you very much for the very nice talk. And please ask question. let me ask one question. So here, from the Brownian SYK, you also need to the disorder average,
Right.
and there and here you consider this melonic dominance, and still there is no melonic contribution. It's suppressed. But when you consider this long time behavior after the scrambling,
Right.
so like the direct diagonalization, maybe that can be taken into account to this non-melonic, but this analytic calculation, how can you take care of this non-melonic contribution?
Right. So those will give you some like additional 1 plus multiplicative factor 1 over n corrections.
So in the Brownian case, what is the order? This 1 over n.
1 over n to the q something like q minus 1. I've got 1 over n correction that multiplying the overall answer. That's it. Yeah.
So you mean the qualitatively it would not be the same changes so much.
Right. So in particular at large n, right? Yeah.
Okay, thank you. And what was this Lyapunov exponent lambda and this Brownian case?
Right. Yeah.
Maybe I missed somewhere.
I didn't write it here.
Okay.
So it's a function of q. Yeah, I don't remember. Yeah.
Okay, so here you don't have any like concept of bound on chaos.
Right. The bound of chaos on this system is there's no particular bound of chaos because there's no energy conservation. Right.
I see. So, but still, you expect that some similar long time behavior also appear in the original SYK or usual K.
Right. One. Yeah. Okay. So this behavior, that is proved by Gu, Kita, and Zhang, because ordinary SYK is also belong to the ladder diagram dominating class. And in particular, they specifically consider large Q SYK, and they can derive the same result, same type of result, the same type of action.
Also, the delta dependence. Where can I see your approach? You said
right. Okay, that's very easy. So at late time, so A is n times e to minus lambda t. So A is very small. So you get some like you get x plus, x minus is order 1 over is order e to the lambda t, right? Order 1 over A. Okay, right? That's where the set point become important. And if you plug this in, this basically is the data. So you got e to the minus delta t. Right? This basically data over lambda L. Sorry. So yeah. So it's e to lambda t, and then you get some factor of this coefficient that gives you e to minus delta t.
So here delta is also should be interpreted as conformal dimension of the
right.
The original fermion.
Right. That I think is still 1 over q. So I guess you can from here read out what Lyapunov exponent should be. Right, something like q minus 2 over q, something like this. Yeah. Thanks. Yeah. So vanishes when q equal to 2. Lyapunov exponent.
Okay, thank you.
In the first part of in the almost first part of your talk, you mentioned about your derived effective action I mean, some scramble mode. You mentioned that this would, how can it be related to some hydrodynamics? How so? Some, can you make it more clear?
Make a comment relation with hydrodynamics?
Yeah.
Right. Okay. Right. So when you do hydrodynamics, you look at path integral shrink characteristic contour, right?
Yes.
And what you do is you basically do the same procedure. You find the saddle point and you look at some one loop analysis. And so you identify the soft modes on this contour, and you write down the effective action determined by your by their eigenvalues. And usually, if you have the system have some symmetry, continuous symmetry, you have some like the soft mode will have some power like a power law behavior. The eigenvalue of the soft mode have some power law behavior, and that's how you derive your hydrodynamic equation. You just write it down, and you get your hydrodynamic equation.
Yes.
Here is the same procedure. You do this, you have some like a saddle on this OTOC contour. You write down, you do a one loop analysis, you identify all the mode. Basically, what you will find is that you have this hydrodynamic mode, but then even lower, there's a nearly zero mode, which is this two scrambler mode. So these are the two action modes on top of this hydrogen mode that you have to add. So those is this is this 2xy mode, and then so if you want to take some correction, you have some hydrodynamic mode. I don't know, some like phi dot squared, some etc. But those will be the hydrodynamic mode living on, for example, this triangulation contour, this contour, etc. But those action will not be the dominating correlators on this geometry because of this this behavior, exponential decay. This coming from the chaotic nature. So in other words, the hydrodynamic mode will give you some 1/n correction to the result I presented here. You can view these two modes as a special chaotic hydrodynamic mode. You use the same procedure in hydrodynamics, you'll find these two modes on this OTOC contour. Right.
So I thought that you tried to mention from some QFT, I mean, whatever it is generally. So then some chaos, how the early time quantum chaos behavior may be responsible for long time some emergence of some hydrodynamics but as far as I understand here, you mentioned that hydrodynamic mode product is just one over n. So so this new mode, you call this scrambler mode in this setup. How this so is it related with some hydrodynamic mode for this scrambler mode or some?
Yeah, you can view it as a special hydrodynamic mode, but only exists on this OTOC contour.
I see.
Right. So you do not see it on the usual shrink characteristic contour. You only on this 4-time contours, forward, backwards, you will see it. Right.
So you mentioned that in the hydrodynamics case, if I also consider this four time Schrödinger characteristic contour, and if I try to OTOC in the hydrodynamic case, then I will obtain
you will solve up if you know the Lyapunov exponent of the theory. Okay. Yeah, you also get this one.
I see.
Okay. Yeah, that's our prediction. We didn't like do any calculation to check that, but that's what we will see.
Yeah, thank you.
Okay, thank you very much for the great talk. Let's thank speaker again for nice talk.